Okay, welcome everyone to the 22nd episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Rupf from the University of Toronto to speak to us about using kinematic measurements to improve athlete monitoring in wheelchair court sports. Rupf is a PhD candidate who has recently successfully defended, so he'll soon be fully awarded the degree. He's at the University of Toronto under the supervision of Dr. Scott Thomas. His research investigates the validity of using a single inertial measurement unit, which is abbreviated IMU, to measure wheelchair kinematics in wheelchair court sports. This work stems from his continued interest in expanding the use of technology to monitor athletes training in Paralympic sport. He's also worked as a sports scientist for several national sporting organizations in Canada, including Wheelchair Basketball Canada. So in terms of the topic today, kinematic measurements in wheelchair court sports have been increasingly used over the last decade to improve the monitoring of Paralympic athletes. Some of the technology and algorithms used help to provide some basic training load information. This information can be misleading. Potential exists to address these issues and to increase the scope and depth of athlete monitoring through the use of inertial measurements, IMUs. While gold standard algorithms can be expensive, they have the ability to identify key game demands as well as monitor key wheelchair movements. Reducing the cost of this algorithm implementation while further addressing measurement errors are important necessary steps for this technology to improve the current approach to athlete monitoring. With that, I'm going to turn it over to Rupf. Please share your screen, and we look forward to your talk. Thank you very much for joining us.
Thank you for inviting me. I just have to figure out how to share the screen. There we go.
Perfect.
So thank you for the introduction there, Dave. So I'm excited to be here to talk about some of the work that I've been doing for the last little bit. And so for today, I figured we could talk about kind of the role that measurements in wheelchair kinematics can have in the monitoring of athletes in wheelchair court sports. To help with this, there's a couple of items that I kind of want to address in the talk. First, after we quickly define a little bit of what monitoring is, we'll look to examine how one of the major components of monitoring, training loads, is used in these sports. This will entail a quick look at some of the internal and external loads that are currently measured. And we'll do this kind of from the perspective of some applied work that I've been doing here in Canada. Once we evaluate some of the strengths and limitations of these approaches, we will look to see how kinematics can be used not only in this process of helping monitor loads, but also in defining demands of the game. And then finally, I'll introduce an emerging term in the field. It's called wheelchair mobility performance, and how this framework can look to be used for monitoring athletes. Within this, we'll look at some methods for measuring kinematics, focusing specifically on inertial measurement units, or IMUs. This look will further examine how we can improve the uptake of IMU to measure kinematics, as well as some issues with the IMU that require some refinements to help improve the validity and reliability of the kinematic measures. So athlete monitoring itself is quite a broad term, so broad that in fact that we kind of have to have a consensus statement put out to help to better define kind of the scope of what the word is. And for those who are interested, this on the screen here is what the result of that consensus or that consensus paper, and it kind of helped. Came out of a think tank that met in Doha and Qatar there a while back. So quickly summarizing some key points from this paper, which will kind of guide the discussion in this presentation. First off, really, what is the goal of monitoring? Quite simply, it's just meant to provide information on whether the athlete is ready to compete that day. This information is typically presented to a coach, and then he or she can make the decision on the athlete's status that day of whether they participate or not. There are a couple of points that we should be aware of. First is that we need to have a way of quantifying the stress of the athlete, which we typically define as loads. These can be done through internal, external loads. Internally typically relates to how the body responds physiologically, which we can usually measure through heart rate or rate of perceived exertions as prime examples of these measurements. There's also external loads, which we typically look kind of through the movement output, for example, monitoring speed in soccer. We can also look to assess this information through psychological measures such as daily wellness questionnaires, profile of mood states, etc. Once we get this information, we need to find a way to monitor this data in more detail. Original work by Bannister kind of brought into the terminology the impulse response modeling techniques that are now seem to be quite common. It's based on a fitness fatigue model and allows us to mathematically estimate an ideal performance state for the athlete. However, other methodologies have kind of also been created and are used quite commonly now, such as the acute chronic workload ratio. And this usually involves comparing an average loading information over a short time duration, usually 7 days, to that of a longer time duration, usually 28 days. This information is typically used to help define optimal performance states or to help identify periods where there might be increased chances of injuries. Thus, the idea of these models is to help present this key information to coaches that will allow the informed decisions about the athletes and their readiness to compete. So quickly, how do we monitor some of the internal loads here in wheelchair court sports? Well, heart rate monitors typically seems to be the methodology of choice, at least here in Canada currently. And we kind of have 3 levels of how it's used. The first level simply just looks at the descriptive intensities of the session. And it usually uses averages or maximums to help describe the intensity of a session. This can be helpful for athletes as they have the ability to understand how hard they work. For example, heart rate can be displayed on a screen during a typical session, providing accountability for the athlete to work at certain intensities. However, this approach may not adequately quantify the stress or load of the session. Consider a 2-hour walk in a 45-minute interval session, which is more stressful on the body. This brings about the second layer of load monitoring, the TRIMP, or training impulse. There are many ways to build your TRIMP model, but the effect of the TRIMP is simply to better quantify the stress by taking into account both the duration and the intensity of the session. For example, with wheelchair basketball, I was using a points-based TRIMP model that was based on the duration spent in different intensity zones. There's pros and cons to all these approaches, but these should be evaluated prior to any implementation. Once the training stress TRIMP was created for each athlete in session, we could then evaluate what this meant for the athletes. We ended up using modified fitness fatigue models in our wheelchair basketball applications, which generate some estimates for fatigue and fitness. However, this model was limited in its scope due to one issue, and this is a lack of performance metrics. This prevented tuning of the model in kind of more the conventional ways that it's used. As a result, this model could only really be used in 2 different practical ways. First, while limited, and because of poor IST integration or sports science, sport medicine integration, it was used a little bit to help inform the coach around potential injury risks to the athlete. Second, this was also used, this was how it was predominantly used. It was used as a planning tool to help inform coaches around macro and micro cycles of training. The model for each athlete was tuned to their theoretical workloads of what I would expect their workloads to be during World Championships and Paralympic Games. And then working backwards from these competition dates, loading profiles for these athletes could be created for both our centralized athletes who trained with us locally or decentralized athletes who did not train with us locally and were other parts of the country. For decentralized athletes, this would inform them of, I'm going to say that the minimum amount of work that was required, because sometimes athletes can be quite lazy prior to them coming to centralization. Or for centralized athletes, this information was used to help inform our coaches around the duration of the work that the athletes required during a typical week. There are some concerns or limitations based on kind of using internal loads to monitor. One of the biggest challenges was what to do with missing data. This happened surprisingly quite often, and for a variety of reasons, including athletes simply not wanting to wear heart rate monitors. 2 issues with the actual data collection itself. So if this happened, so as this was happening, well, how do we deal with it? And there was kind of two approaches that we kind of looked to deal with missing data. I think that would be of interest to this group. First, we evaluate the typical distribution of the athletes, specifically around the average of the team. And for most of these people, what we noticed was at least a normal distribution around kind of these averages. So we quickly generated a random number within each of these distributions centered around the team average and use that to help fill in the missing data points. However, this approach also was session averages themselves were also dependent on which athletes we actually collected data from. So another area we were starting to explore in a little bit more detail was trying to figure out how each player impacted each other player's contribution and using that as a means to fill in the missing data points. So in terms of other issues, limitations with the internal loads that we experienced here was that of software and hardware selection. So we used polar heart rate monitors as our method of, or as our hardware of choice. And the sport had actually invested quite heavily into these monitors for everyone in their program. So they invested heavily into the chest straps specifically. However, they didn't necessarily invest in the software application of it. And the result was that we were only able to use their freeware, which allowed us limited information to collect, specifically around the time spent in each intensity zones. And further, the intensity zone could not be manipulated by changing maximum, but it could only be manipulated by changing the maximum heart rate. Thus, specific individual zones could not be generated. And so what you do when there's not a budget for a proper software to help collect this information. And this is sort of a challenge within Paralympic sports. Finally, the modeling approach to monitor training load itself is limited. As described earlier, it was a planning tool and really nothing more. Without performance metrics to tune the data, this approach is limited in its ability to be used as a performance monitor. This means that,
can I just stop you there? So this is all very interesting. One thing I was wondering about, so heart rate in Paralympic athletes who have autonomic deficiencies, how does, did you observe any effects? Like, did they have abnormal heart rate responses, some of them?
So typically what you'll see first and foremost, so let me phrase that, in wheelchair basketball, there is a range of issues or a range of kind of injuries that occur. So for most like amputation or people who've had amputations or have kind of acquired their injury over the time frame through non-spinal, non-SCI, their heart rate responses were fairly normal, and you could treat them associated like very much how we would treat kind of able-bodied athletes. For those with SCI, definitely, and depends on the level of the lesion. There definitely could have been some issues with the heart rate response specifically. From observations that I had, we would see normally increased heart rate responses, so increased maximum heart rates. But in terms of a range of values for different types of intensity, that was still present. So we could still tune our time in our various intensity zones according based on kind of their heart rate responses. And so we kind of played around with this a lot, kind of through using kind of traditional treadmill type protocols with increased workload, because we are lucky enough to be able to put our athletes onto treadmills and do kind of normal or maximal exercise type testing.
Right. Fascinating. And then there's just a second question about the IR model. So were you using sort of just a guesstimated parameters and just running, so you're running different training load profiles and seeing the approximate effect and planning a taper accordingly?
Yeah, so for kind of each person, I kind of got a general sense of kind of what that load might be, and kind of use some sort of basically a qualitative type index, which I called the grumpy mood, and how grumpy they got kind of within their competitions. And then from that, that was kind of what I used to help tune a model, just generic parameters put in initially, and then from there worked backwards. So not ideal, as I said, because we don't have anything else except the grumpy metric, as I called it, to help tune it. So that's why I left it more in the realm of planning, just to give ballpark information.
And then how different were the athletes for their models?
They weren't too different, to be honest.
Yeah.
So it really depended on kind of just the amount of time they spent, the amount of information, the amount of data we were able to collect on them. Like the more information and the more centralized they were and the more willing they wore heart rate monitors, the better we could, there's more differences, but for the most part, I was using pretty much similar parameters throughout.
Excellent. Thank you.
So next, so internal loads themselves, there's through the conversation right there with Dave, some challenges associated with it. And for the most part, you're probably only really looking at that as an injury prevention model, moving kind of and being able to track that. And that probably provides a maybe a better way of looking at it because of the inability to quantify performance metrics. So that leads then external loads, and how do we measure external loads? Well, when possible, we like to measure external loads with power, as this helps express a measure closer to that of stress. Power, however, is not obviously measured directly, and it's either derived or assumed to come from measurements of force or speed. So can we measure force in wheelchair court sports? Well, the answer is yes, but is it practical? The answer to that is no. And this happens to mostly come from kind of commercial products to how athletes push. So there are products out there that allow measurement of force when you push the hand rim, and there's strain gauges inside these hand rims that do measure the force specifically. But in wheelchair rugby, the competition wheels don't actually have a hand rim, so that kind of eliminates that ability to measure force. And then also within wheelchair basketball, athletes don't even use the hand rim; they push from the wheel. So while you can develop hardware to be able to potentially be able to use in kind of small scale type testing, the ability of introducing this into loads until commercialization of any product occurs makes it very minimal. So therefore,
why do they use the wheels and not the rim?
a combination of it's a good question. It's one I've never fully explored with the athletes, but just observations. Hand rims are closer to other wheels, which means your hands are likely going to get crushed.
Right.
There's more chance for generally finger injuries that might occur because your hands are getting caught in between the wheel and the hand rim itself. So it's more dealing around those kind of issues.
Gotcha. Yeah, that sounds very painful.
Yeah, it definitely is. So this basically then obviously means that speed itself is kind of the way we can look to generate external loads, and hence the reason why kinematics is kind of a way forward within wheelchair court sports. So can we generate measures of power within wheelchair court sports? Let's take obviously a closer look at this, and this is sort of some work that was done by some colleagues in presentation that we went through a local conference called SPIN. And here we can see that we can generate estimates of power through velocity measures. These are just the outputs specifically, but we can see during a 20-meter sprint, in a linear direction, we can generate at least estimates of power. And this is work that's been similarly done through other work as well. And then kind of there's lots of examples in the literature around being equations to deal with power, which is where this information came from. But there are limitations to this. And let's take a look at some of these limitations. So traditionally in other sports such as footy, we can measure the speed of the athlete and then use this information to help us understand the intensity of the zone. Typically, this is done with coming up with some way of identifying zones at different intensities and measuring the amount of time they spent in these zones. And then from this, the load can be further quantified. This, however, makes the assumption that speed translates directly to force, and this assumption works fairly well in field-based sports, but may not work as well in wheeled sports, does it? And so in this example here, if I were to show you the speed profile for a cyclist who performs an hour of work, what would you say the workload is? This could be a track athlete who, after a long warm-up, decided to work a little harder. So this could be an example of a power output. Or this could also be an athlete, climbing the Alpe d'Huez. And as a result, the speed profile could actually be inverted on the uphill and the downhill portion. So in cycling, we're lucky enough that we can quantify this work because we can measure the force and express it as power. Therefore, in cycling, we can measure external load by using power without requiring speed. However, in wheelchair sports, this relationship does not exist, and currently we do not know when and where force is being directed. Two such examples illustrate this point. For example, this figure here shows a 20-meter sprint. You can see where the athlete sprinted and where they did their work. But this figure also shows an athlete coasting back to the start line where they really didn't push whatsoever. So identifying coasting and speed profiles hasn't really been investigated in the context of kinematic outputs, although it's been estimated this can account for 30 to 40% of all linear movement. The second example is rotation, and around 30% of basketball games may involve rotation. However, forces in turning are not necessarily well understood. In data I've collected, we can see that the total force during pivots are similar to peak forces generated in sprinting. However, currently, we do not know how to quantify this intensity in kinematic profiles. Thus, when we look to use speed to help measure intensity and loads, we have to be careful in our interpretation as illustrated by this final point. In some pilot data I collected during some basketball scrimmages, I manually identified high-intensity movements using video. We can see that upwards of 70% of these movements involved 1 or 2 pushes. However, when I synchronize this video data to speed data using existing techniques to identify high intensity with speed profiles, only about 5% of the high intensity movements I'd observed were actually identified. So our ability through these speed profiles to identify high intensity work still requires a lot of work. So if kinematics aren't necessarily useful at this point in time in measuring external loads, what can they be used for? Well, maybe instead of they can be useful in determining demands. This is highlighted by a paper from Dr. Rink van der Slik. In this paper, he used IMU to derive speed and rotation metrics. In defining upwards of 30 measures, he used PCA and then defined 6 variables that were of interest, describing around the movement of the chair that helped describe a lot of the variance. This included 3 linear and 3 rotational movements. Further, he observed that these movements differed between different classification groups, with those having more ability to perform these movements faster. Thus, in this context, kinematics can be quite useful. We can also see this when we look at some testing protocols. This next example comes from some work performed by Dr. Klimster and Dr. Chang Sai and presented at an ECSS conference in 2019. Here they measured the kinematics of a commonly performed test in one of our national programs, the agility test. We can see this continued profile of the kinematics, both the linear and the rotational in the figure there on the right. And from this, we can kind of get an idea, once we factor in the different segments of the test, that we can get quite a lot of information based on the completion of the different sections. So similarly to Dr. van der Slik's paper, PCA and factor analysis was performed. And from this, some key variables that describe the test were performed and were identified, which once again included the importance of rotational movement. And I'm just one last point here is a kind of potential extension that hasn't been done. This was just a very crude analysis I did a while ago, and I just put it in here just to highlight maybe where we can extract more information from. And so using kind of the same agility test, but using different data sets, I quickly looked to see how some of these components tracked over the course of a test. And I said, well, this methodology that I'm using here is a little bit limited. The point really is to demonstrate that different factors might play a different role at different times during the testing process. And if these points can be identified, then we can mine more information. And so using this kind of rudimentary example, we can see that there may be something further to explore roughly halfway through the agility test. Kinematics kinematics might also be important in the development of a new framework known as wheelchair mobility performance. This construct suggests that the movement of the chair is based on the interaction of the person pushing the chair itself, and the demands of the game. However, at its core, wheelchair mobility performance looks to identify a movement pattern, then the measure and its kinematic outputs. And any interventions based on these three pillars of mobility performance is considered successful if the chair moves faster. So can we identify movement patterns? Two examples highlight some patterns we can detect. First, pushes in a linear and straight direction. Dr. Vanderslick has performed some work in this area, highlight that through the acceleration profiles, that acceleration profiles can be used to identify pushes. However, this process does not identify contact times as shown in the acceleration plot, where these dots represent hands-on and the hands-off during the push phase. Further, this method is limited to straight linear pushing, and we cannot identify pushes during turns. We can also see that simple movement types can also be classified using simple thresholds on speed and rotation data first used by Dr. Vanderslick. We can identify movements such as straight linear movement, turns, backward movements, and pivots. The bottom figure here shows this classification process during the agility test. So with an ability to classify based with movement patterns, the kinematic of these movement patterns can be evaluated. Thus, by tracking the progress of these movement patterns, this does provide a new and what I like to say exciting way for help us to monitor athletes in wheelchair court sports.
So Rob, sorry to interrupt, but is that through the gyroscope then? You're using the rotational data?
Yeah, so this is actually through methodology. I'll be describing that a little bit later.
Okay.
So hang on there, Dave.
All right, no problem.
Because the next portion here is how do we actually measure these various kinematic patterns? So typical ways, there are some ways that have been used, or one way specifically is using technology that helps us find the position of the chair, such as local positioning systems. These systems triangulate the position by measuring the time it takes for a signal on the chair to reach the base station. And of course, here at the intersection of several of the resulting time of flight circles is used to determine the position of the chair. And the position of the chair over time is used to determine speed. Data loggers, reed switches have also been used to measure the time to complete revolutions of the wheel, and both forward and backwards motions can be generated. Both of these methods, however, do not measure rotation. And as we've seen earlier, that is an important element of the game. And this makes it difficult to measure mobility makes it difficult to measure mobility. So then this is sort of where IMUs can come into play and why they represent a way forward for measuring kinematics. Simply, the major reason is that they can measure both speed and rotation. And while there are many algorithms and approaches, I consider the one developed by Dr. Vanderslick there as the gold standard methodology there for measuring kinematic measurements in wheelchair court sports in the field. This 3IMU approach uses 3 inertial sensors. The sensors placed on each of the wheel hubs, and the third sensor placed on the center of the frame axis. The algorithm also has 4 distinct elements that I want to quickly highlight. Here, the first is that, it generates is what is known as the true wheel speed during rotational movement. And they call this the Pansiot equation, which was first introduced by Pansiot. Because of the wheel camber, the frame rotation contributes to the angular wheel speed, and this impacts the contribution seen in the pivots here. And the measured wheel speed gyro is actually different than that in the true wheel speed in both 3IMU and kind of a 1IMU, seen in the difference in the amplitudes here on the far right. So we can see the impact of just measuring gyro versus that of using the contributions associated because of the camber. And so gyro itself, using a gyro isn't an effective way of measuring wheel speed. A second attribute is that of a complementary filter. This is meant to help stabilize the wheel speed signal by adding degrees traveled during each sample between the accelerometer and the gyro itself, highlighted there in the green box. The third attribute is the acknowledgement that wheel speed may not be equal to wheelchair speed. And this is because the speed at each wheel will differ from that at the center of the frame when the wheelchair rotates. There are two components that need to be highlighted in determining wheelchair speed using this gold standard algorithm. First, this estimate is generated at each wheel by fusing rotation and wheel speed data. Second, an averaging technique is used to merge estimates for the wheelchair speed derived from left and right wheels. This approach further helps stabilize the output. The final attributes area is the skid correction, which compares the frame speed generated by the center of the chair estimate with that of the acceleration derived from the frame-mounted IMU. This approach has been shown to provide excellent levels of agreement with motion capture technology during small-scale movements and has been used during testing in games in multiple amounts of wheelchair court sports. So, and then to answer your question, Dave, is that this is in a lot of the studies or a lot of the information I was presenting beforehand. This is the algorithm itself that was being used.
Yeah, awesome. Thank you for going through that.
There are some practical issues, though, using this approach. So not only must each chair be measured for certain parameters, such as the wheelbase, the wheel size, and the wheel camber, but there's also the failure if you don't synchronize all three IMUs. This can affect the reliability of the data. To outfit each athlete with three sensors is also expensive, can add thousands to each team budget, which, as identified earlier, is a bit of an issue. Further, the volume of data generated by each sensor is expansive. Currently, not only are several devices required to collect data, adding further budgetary costs, but the process of downloading and analyzing data is quite time consuming, with upwards of 1 hour required to generate information for one session for a team of athletes. Thus, the cost of this approach, the chances of user error and setup, and the time required to generate this data all represent significant barriers for teams with small budgets and manpower to adopt this technology, and hence then reduce its actual uptake in application. So this has then kind of led to my area of research here, which is trying to find an alternative approach, specifically using only one IMU to see if we can help reduce some of these barriers. And so this algorithm here, the process used one IMU placed only on the wheel hub. And by using the magic filter, we can get measures of both it measures the attitude of the wheel. And then by deriving tape iron Euler angles from this, we can generate both wheel speed and rotational speed from that. So essentially, we're both getting wheel speed and frame rotation, which is significant. There are several potential advantages of this approach. Primarily, it will reduce the cost associated with using this technology. This is accomplished not only reducing the number of sensors, but also in terms of the additional devices to capture data. It further reduces the chances of user error and setup as less sensors need to be initialized. However, there are also some relative unknowns in this process, especially in comparison with the 3IMU. First, it can replicate the Pan-seed equation, or can it? This method should be able to handle drift better, as it is an adaptive filter, but does it? And third is the estimate of frame rotation measured at the wheel, an actual viable measure. And can it provide a robust method to measure the wheelchair speed without the contribution of data from a second wheel? And finally, how does skidding impact these values? So I kind of consider this maybe a bit of a rite of passage, but for the next couple of slides here, I'll quickly be talking a little bit about my PhD and the kind of output of those results. So basically, 3 papers were used to help ask the question is, can this one IMU approach generate good kinematic data? And the first paper specifically focuses on directly on comparing one IMU with 3 IMU algorithms through some testing protocols measuring both linear and rotational movements. The major goal was to determine whether there was good agreement in angular wheel speed. And the second goal was to see if frame rotation measured at the wheel is equivalent to that, or to the measurement occurring at the center of the frame. And then a third goal was, can we get a very good or a good reliable estimate of wheelchair speed? In the second paper, looked to directly evaluate linear wheel speeds, and the conversion between the angular wheel speed and linear wheel speed depends on the wheel size parameter. So we're actually getting into the parameters used and errors associated with that. So therefore, any bias could likely be associated with poor chair measurements. And a secondary aim was to determine if one IMU could also detect simple movement patterns. And the last paper here was basically asking a practical question, was how low could our sampling rates go before the kinematics data start to become unreliable? And once again, these questions are specifically looking at trying to reduce information being sent, which would help reduce cost associated with any commercialization of this process. So really quickly, a lot of this work here was centered around two tests: a sprint test and an agility test, where we had different segmentation of the information that we could evaluate at different time points. Okay, so the primary question in kind of our first paper here was whether wheel speed generated from one IMU replicates wheel speed generated from 3 IMU. What we kind of see from this is that low root mean square errors and R squared values suggest that we get good levels of agreement even in rotational movements, which is good. And that the added bonus is that unlike the 3IMU approach, this wheel speed was actually derived without the measurement of wheel camber. So we're essentially getting rid of one parameter that needs to be measured and taken in, which is a good thing. The second question was the level of agreement between 3IMU and 1IMU wheelchair speed. The study suggests that good levels of agreement also exist. However, further algorithm development is likely required during turns to reduce both the higher error rates and limit variability in measurements when the IMU sensor is placed on the inside or outside wheel. The second paper looked directly to estimate how well one IMU can generate time data, an integral part of adopting this into any testing protocol. And for sprints, we see good to excellent agreement across all time intervals. However, a small bias does exist in the time to complete 20 meters. The poor agreement at the very first time point there at SS1 is due to more of a methodological error than anything else. However, the bias, one of the key aspects here is that we do see a bit of a bias, but that bias is eliminated if we actually adjust the wheel size. And here, when we reduce the wheel size by about 1 inch, we start to get values that are more realistic. And while we haven't, unfortunately, been able to retest this over the last little bit, we do actually see that when we load if someone sits on a wheelchair and we measure their wheel circumference, they lose about 1 inch off their wheel size. So basically, the bias might be accounted purely from a very poorly measured wheel size. And then finally, for the third paper here, when we reduce sample rates, there is evidence that the wheel speed is reduced, and therefore at slower sampling rates, the metric likely has some issues converging to the actual attitude, resulting in greater errors. Further, there's also some evidence to suggest that proportional errors likely exist once some sort of threshold is passed. And then, so basically what the last part of our presentation, or the last part of this kind of dissertation discovered, was that we really shouldn't be going below 50 hertz in our data collection, where normally a lot of the IMU collection takes place at around 256 hertz. So once again, this is just another way of saving data points. And then so overall, what did we get kind of from this work was, well, one, that we can get pretty good to excellent agreement in both our speed and rotation signals when we use kind of this one IMU approach, so only using one inertial measurement unit. So that's actually very good. So it means we get a really good estimate of kind of our wheel speed, and that our data fusion itself is pretty good. And then we can also do this probably at lower sampling rates, but there's still some work that needs to be done. And so while we see there's good agreement, a simple question, well, why would it be good to kind of use only one IMU? Well, the answer probably, as I've kind of been alluding to, it just helps speed up the workflow. And we can see in the data collection process here, between the one IMU and 3 IMU approaches, is that we eliminate one box, so we're saving time. However, these boxes also highlight another area of interest, and that's how we collect data. There still exist commercial challenges in how we collect the data. Do we stream the data? Do we log it? Do we use Bluetooth, Wi-Fi? Do we collect data on smart devices or on a laptop device? If they're all present, these all represent different challenges that need to be considered. But as I said, the advantage of this kind of one IMU approach is that we reduce the amount of information that requires to be transferred, and this can create more manageable solutions moving forward. So I've been talking a little bit about kind of parameters, and so this hopefully can maybe understand or highlight once again why that's important. Kind of from that second paper, we saw that wheel size itself can introduce quite a significant bias into a 20-meter sprint based on how we actually, or based on the measurement itself. So if we can start reducing these errors, or we can start minimizing their impact, that's probably a good thing. And what we kind of found was that these parameters do, specifically in the one IMU sense, but also I'll show you some stuff around how in through IMU. This also probably produces the largest source of error in measurements of our kinematics. So great thing about the one IMU is that it appears to eliminate the need for measuring wheel camber. And then kind of, as I mentioned, wheel size itself, we need to either rethink how we measure wheel size. Some of the suggestions or observations we've made is that if we actually measure the wheel circumference under load, that would be a better approach. So that could be something that could be used, or we can start to look into other areas. For example, how robotics looks to tackle some of these same problems in their measurement of kind of both wheelbase and wheel size, where they have their robots go around in a square circle, highlighted there kind of in the bottom right by the blue circle. And then they retroactively or minimize the differences and errors around that course until to get more of an effective wheel size and a wheelbase. So these represent some calibration type procedures that can be looked to be introduced. So there's still some limitations in obviously measuring our kinematics during rotational speeds. Specifically, IMU are limited in their ability to measure horizontal translation of the chair frame as we see during skidding. Combining additional outputs such as LPS with IMU can be one way that we can help to improve these errors. So the addition of new technologies. Part of the question might be, why look to do this? A simple answer is that we might want to have better assess movement so that we know how and if any intervention is actually working. And specifically, we want to have the ability to evaluate this any intervention in 2D space, because success is based on gaining a spatial advantage over another chair. An example can be seen when we're looking at U-turns. This is a common movement in basketball to help an athlete to get from one side of the opponent, or from one side of opponent's chair to the other. It involves athlete pulling backwards, pivoting, then pushing forwards. And we can use the one IMU to plot the movements in space and which we call the trajectory plot, which this is an example of here. And when we look at 12 consecutive U-turns performed consecutively, we can see that while similar, there are differences in the trajectory plots over time there. And then, however, our observations are also blurred by a bit of a drift here in the IMU output. And if this drift can be minimized, then we can improve our learning about how the athlete moves in space. And we can gain a better understanding of the spatial advantages as we start to classify this movement quality. And so basically, if we can work to identify, or towards both identifying more complex movements such as U-turns and have improved the measurements outputs, we can imagine a scenario then in which an athlete here with the center circle has to navigate his way through the 2D space for an offensive scoring opportunity. In this scenario, we could determine the types of movement the athlete performs to generate the scoring opportunity. We could then determine how successful these movement types were based on previous knowledge. Then we can start to automate whether some of these movements constitute an offensive or defensive pattern. As an example, and then maybe with some luck, we can start to investigate what types of movements can lead to successful possession outcomes. It is important to state that if this work is possible, the depth that the kinematics can bring to monitoring wheelchair court sports would be impressive. Instead of measuring just loads, we have the ability to use this information to build both technical and tactical skills. So this would be the ideal dream. So can we actually correct these algorithms to help define these spaces without the use of additional technology? Well, we observed from the 3IME algorithm, the incorporation of better handling as wheelchair speeds are derived from both the left and right wheel. So in the case of kind of the one IMU, if the wheel speed can be generated for the opposite wheel where the IMU is not attached, then maybe we can create better error handling mechanisms. And to perform kind of rudimentary check on this idea, we help to generate a perceptron model. Oh, sorry. So in this case here, these are two specific examples of where we're seeing some issues with the rotational movement. So when we specifically look at turns, we can see on the left, we're actually generating a bit of a negative speed in the middle of a agility test, which if you were observing the test itself, you would see is not necessarily something that's possible. So why is this the case? And this technique itself then is involving where this was a technique that was observed and it was only observed in wheelchair rugby, where the athlete used a lot of force on the inside wheel of this turn and essentially stopped the wheel. And this was what he used this as a pivot point to be able to turn around through the agility test. However, he must have pushed so hard that he actually moved the wheel backwards in that situation. And so here we get an example of where some of these algorithms might not be very reliable. And so something to consider. And then this U-turn example here, once again, this is a second an example where we've seen where kind of these algorithms can start to fail a little bit. And this is here the athlete performed 3/4 of a U-turn and then pushes in a linear direction. And then during this movement, the speed profile during the linear turn is dependent actually on the U-turn direction. So what I mean by this is the IMU on the wheel that goes backwards, negative speed is generated. And if the wheel that goes forward, positive speed is generated, as you can kind of see by those two figures on the right. And thus issues with the fusing of the wheel speed and rotation appears to be the problem. And so, as I said, it's if we can generate more error capabilities, whether it's in the 1IMU or 3IMU, we might be able to address some of these issues. And then, so we did a rudimentary check on this, and we looked to specifically, we played around with artificial neural networks as a way of maybe estimating opposite wheels speeds. And so this, when we did that, we happily, or to our happiness, this kind of rudimentary process here showed positive results with the little data that we did have. And then during turns, we can see that we avoided a negative speed during the turn, which was positive. And then further during our U-turn data and a pivot to the left, we can also see that we avoided a negative speed. And so this represents a more realistic set of data. And so there are ways that we can look to approach some of these limitations, and maybe our ANNs are one way of approaching that. So incorporating these algorithms into games, however, remains kind of the important element in using kinematics as a monitoring tool. So the question is, can we? And the answer is sure, why not? It's already been introduced in the Canadian sports systems to measure basic kinematics parameters. To help us measure loads. Further, the issue with algorithm choice or errors does not appear to be any sort of mission critical failure. And so here's some game data that contains some basic information from two halves. And they process the wheelchair speed using the 1IMU algorithm, and then also simply just using measurement speeds from the gyro data itself. So two different algorithms altogether. However, when we change the wheel size, so we see that the difference between those two algorithm approaches isn't very much, maybe about 1% difference. But when we change the wheel size, so once again, a parameter itself, the difference are substantially different. And once again, I view this as kind of the suggestion that at least for some metrics, we really need to improve our wheelchair parameter estimates, as these parameters represent a significant source of error for a lot of these global measurements. Okay, and to conclude, we chatted about the role that kinematics can play in athlete monitoring for wheelchair court sports, and then traditional methods of measuring internal loads likely offer a better way of quantifying stress during a session than using the kinematics, and this is primarily because we don't have an ability to determine where athletes work. However, kinematics can be used to help identify game demand, specifically the importance of rotation. Further, as we continue to build our methods of automatically identifying movement patterns, we can start to monitor how training impacts the athlete's performance, added additional levels of information to provide to coaches. Therefore, if we can reduce some of the barriers of using IMU, we may be able to increase its uptake in the sport. The one IMU solution is something that may start this process. However, this research also identified the role of wheelchair parameters in error handling, specifically during rotational movement on generating reliable and accurate data. However, the depth of this information is impressive and can greatly enhance our ability to monitor athletes. So at this point, just quickly some acknowledgements to different people who've helped through this research, and we can take some questions at this point if there's any. Thank you guys for your time.
Thanks very much, Rob. Okay, so I'm opening the floor to questions.
Sure, I can ask one. Hi, Rob. Thank you for a nice talk. Our group is interested in some of these problems, and I was wondering if you just could give me some high-level opinions on what you believe on accuracy for optical, cameras and optical recognition software versus GPS versus the LPS that you're using. With our cameras and optical recognition software, we think we can get velocities to accuracy about one tenth of a second when measured in 1/10 to 1 decimal place when we're measuring in meters per second.
Okay. Yeah. So in terms of kind of error rates that I've been exploring and playing with, within the 1/10 to 2/10 of a second, I guess it really depends on kind of the metrics that you're looking at. If you're really looking at just kind of global averages and global speeds and various aspects like that, I think the range of error in kind of the measurement techniques can be quite large, probably even getting up to 0.3 of a meter per second if you're looking at speed. And because the differences themselves are actually, I use the example of the gyro algorithm when looking at games versus the IMU procedure, which should theoretically for every rotation should produce larger differences in speed. But as you saw from that, the average in speeds was actually quite low, if anything, like a 1% kind of difference. And with average speeds around somewhere in the 1.5 meters per second within the game. The ability to have larger errors, I think, can exist. But basically, if you're looking for specific movements, 0.1 seems to be about the average of kind of what I've seen. So in Dr. Rink van der Slik's work, kind of they noticed a difference around 0.1 meters per second between motion capture systems and kind of the IMU techniques. If we can get obviously lower than that, that's fantastic. So I think if we were looking for specificity within specific actions, obviously the lower the better is the way I'd kind of look at kind of that error rating. And so the fact that motion capture LPS kind of systems, they tend to be my work with the LPS would suggest that the error rates are fairly low in terms of position. It's just a matter of how they align as you start summating them over time. So I don't know.
So those three methodologies, would you say LPS is the best?
So I would look at LPS itself is defined and everything's derived from finding position. So so in terms of looking at my experience specifically is mostly with LPS and then IMU, so I can't actually talk about motion capture systems with that there, Tim. But it's if I want clarity on where they're actually at a specific time, not necessarily which direction they're facing, but where they're at in a space and point in time, then I'd be more interested. I'd lean more towards LPS systems at that point as providing better picture and more clarity than using IMUs at this point in time. And then, but that comparison between IMU and or LPS versus kind of more motion optical systems, I don't have a good feel on. So I don't know if I can answer that question, Tim.
Okay, thank you very much.
Rob, I have a question. So you mentioned like the parameter measurements. So you have to measure stuff on the chairs in order for these algorithms to work. And you mentioned that these are challenging. Why is that? Why is it so hard to get these measures accurately? It seems to be fairly straightforward, at least my uninformed eye.
Yeah, it's so I use the example of wheel size. So the two methodologies that are typically cited in the literature is they'll either take the wheel size of the manufacturer, what they provide, or they'll just measure the diameter of the chair itself. The issue, of course, is the tire itself. So when you sit on the chair itself starts deforming. The tire itself starts deforming, so the actual running circumference changes. And the fact that the wheel itself is already on a camber, what is that exact aspect? And tire pressures and stuff might even make more of a smaller change, minute change. But as I said, the difference between measuring the actual diameter of the wheel to when they actually roll out, it almost seems to be that the effective diameter is decreased by about an inch. So our measurement techniques that have been explored are previously haven't been very forthcoming in the literature. So these were kind of the practical examples that we've been kind of discovering. So as it comes to wheel camber and then wheelbase, once again, I would probably say like on the general, when we take a look at that initially, it sounds great. But once we start going through turns, how various weight shifts that might occur within that might affect some of the parameters in the running track specifically. So when we want to start getting into more detailed nuances, that's where some of those issues are really going to start to play and have a role.
Is it like possible to reverse, like, so you have an estimate that effective diameter is reduced by an inch. Like, is the IMU data, especially if you have three of them, accurate enough to actually fit those parameters instead of having those independent measures?
Yeah, so I think kind of those from what I understand of your question, Dave, there's more of this, what kind of calibration procedures can we look to do? So the IMU itself, because of the way most of them are set up, they're mostly just interested in measuring the rotation of the wheel. So it's really the angular rotation that we're really getting that measure of. So it's now because of the issues of kind of integrating or basically changing our speed signal, because that's what we're getting into position to maybe help adjust some of those questions on the fly. I think that's where that becomes more of an issue. But that would come into some sort of automated calibration procedure. And I kind of highlighted a really small study by Krivich. I can't pronounce his name. I do apologize to him. But it's kind of just, we can set you through a course and then that could do the automatic calibration procedure. But the IMU itself is going to have a very hard time of determining the displacement because we are just really measuring the angular movement of everything, not necessarily the linear displacement.
Okay, yeah, well, seems complex. Okay, is there other questions from anybody else? Okay, I think at this point then, I will stop the recording. And before I do, I would just thank you, Rob, very much for introducing us to the world of wheelchair court sports and monitoring athletes. So that's really fantastic. Appreciate your time.
Thank you for having me. Thank you for allowing me to chat about this. So.
Great stuff. Thanks again.